Um, Today is experiment 10, and this experiment here is about calorimetry here, experiment 10. Calorimetry here, guys. As you can see, it's calorimetry made of two phrases. It's calorie and metry. Metry to measure. To measure what? Calorie. Calorie is heat, the unit of a heat, correct? So, when we said that, as there's two phrases here, so we can see that 1 calorie here is 1.84 joules. Today you will be working, I think, with all your work, because we want to see the heat of solution in joules per mole. So in joules, so we'll be working with joules here. Okay, guys, capital C, this is small c here. Capital C, like this one here, that's for food. For food. Okay, here we have the heat per joule per mole. In the food, heat calories, capital C per serving. How many serving per serving? Here, there per mole, and per food per serving. So, in this experiment here, we'll learn about 3 items or 2 items, and then we'll use the third item, which is will go all over with us all the time. We'll determine the specific heat of a metal. So that's the major task today. Heat, specific heat. Sorry. Let's do this one here, specific heat. The specific heat of a metal. Okay, so you have there, I think you have, if you look there, you have a metal shots. I think they look like aluminum, but check it out. There is no cylinder one, but you will use metal that's really like a shots. Then the second one here, heat of a solution of ammonium nitrate, and that's just for ice, the ice pack you buy from the pharmacy. So that's an endothermic compound. Endothermic means endothermic compound here. So whenever you have ammonium compounds, in order to dissolve them in H2O, they will acquire heat from outside. They will acquire heat from outside. So those 2 major ones will be measured by homemade coffee mug, as you see here, and homemade, I would say, coffee cup, or whatever you call it, or mug. So this one here, the third assignment of today, we'll learn how much heat is this calorimeter is absorbing. Anytime you work with it, it will absorb part of the heat. We call it what? The third part is specific heat. Specific heat, we have to determine the specific heat of homemade calorimeter. Okay, guys, so this is very, very important 3 items, and the third item here will overlap those 2, correct? So let's start. Can I take this one out? Everybody has it? Everybody has it? Everybody has it? Okay, let's take this one out and see what the definition of specific heat. And then I'll give you my own definition of specific heat. We'll not find it in the procedure textbook. So, what is specific heat definition? Well, it turns out from the the books, your textbook here, specific heat is amount of heat needed. That's a normal just definition, correct? Amount of heat needed, here it is to raise the temperature of 1 gram of matter, any compound, any matter, anything, 1 degree Celsius or 1 degree Kelvin. That's by definition. If I use a heat that will raise the temperature 1 gram of a matter, any matter, correct? Metals, solid, liquid, gas. This one, it has to be 1 degree, and that's the amount of the heat I need to raise the temperature to 1 degree for 1 gram of a matter, just only 1 gram. And therefore, you'll see the units of specific heat will be what? Will be units here will be calorie per small capital. That's a small s, the small c, not capital C, small c. The capital C for the food, you said, correct? Yeah, that's small c. Calorie per gram per centigrade. 1 gram, 1 centigrade Celsius. Now we can, today we'll be working with joules, capital J, joules, 4.184 joules, 1 gram per 1 centigrade Celsius. And that's by definition, the amount of energy needed to increase the temperature of 1 gram of the matter, how much? 1 degree. 1 degree Celsius or 1 Kelvin. Okay? Good. Okay, so that's the definition. Now, how in the world I can really give another definition? That's the master definition. That's from the book. That's the highest well-known definition. But how I can visualize it in my brain? What's really specific heat? I ask another question. If I have solids, let's look at this. I have solids, I have liquids, I have gases. Which one of those states of matter will keep the heat with it for longer time? Gases, liquids, or solids will keep the heat? Solids, that means can I do the heating of our building with the copper wire? Solids. Liquids, can do oil, use oil to heat the whole building? What I use here?
Oh, gas.
Gases, methane, correct? Natural gas. I use methane. Why is that? They have highly specific heat. So the ability to retain heat, that's a specific heat. The ability, that you'll not find any textbook. So I'm not flattering myself, but that's not in any textbook, guys. So we did define it as in the book for your exam, but then you have no clue what really is specific heat. Now you know. So the ability, that's not copyrighted, but that's maybe copyrighted. Dr. Ataya here. Dr. Ataya's definition. Copyrighted here. But that's just for fun. No, it's not copyrighted. The ability of a matter, any matter, whether it's solid, liquid, gases, plasma, the ability of a matter to retain heat. So if I heat a metal, correct, copper, and leave the metal out for a couple hours, it will cool down, correct? Less than 1 hour maybe, will cool down. Liquid will take, the oil will take maybe more hours, more time. But the gases will stay for a whole day warm. The ability to retain, to keep the heat, to keep the heat within its molecules. So correct? So this is the specific heat. Now we know the units of it. Now what is the formula we can use to determine the heat? Can I take this one out? Take it out. So we know that gases higher, yeah, higher specific heat, higher specific heat. Solid are the lowest. Higher is lower, or highest, lowest specific heat. The solids the lowest, and the gases are the highest. Liquid moderate, in between. The values are in between. But the gases are they have the greatest ability to keep this heat. Correct? So let me take this one here and then look at the formula we'll be using. So the formula we'll be using now, in books, some books they put Q for the heat. Some books will put some Q here. Some books will do E. Some books will do H. That's all meaning the same thing. Heat is energy, correct? Heat is what? Is energy, meaning that's the same thing. Now your lab procedures, I think they do small Q. Let me just check if that's really true. What type of Q they are using? Here it is. So they are using what Q they are using? Small Q. But you get the idea. If you open any book, don't be surprised to see it E, see it small Q, see it larger Q, the bigger capital letter Q. Enthalpy H, E. Those are meaning the same thing. So I will go back by your procedure. So I will be using this one here. So we'll be using Q. Correct. So we'll be using Q. So Q is will be how I get the specific heat. I have to determine the heat here by mass of the matter itself I'm using, multiply its specific heat. I'm using different maybe symbols, but you can see they use symbol a different one inside your. This is specific heat. Here it is. This is M, mass. This is specific heat multiplied by delta T. Delta T here is given this difference in temperature, difference in temperature. So delta T always is designated T final minus T initial. Okay guys, so how I can get the specific heat here? So I can work it out the other way. From here I can say, well, out of this one here, the specific heat is Q divided by mass over delta T. Okay guys, that's how we determine the specific heat of the matter, any matter, whether it's solid, liquid, or gases. Okay, so now the first thing here, we'll have to determine the specific heat of the calorimeter itself. That's a problem, because anytime you use this calorimeter, bless you, whether this is homemade, whether it's even manufactured calorimeter, the first thing you do, you calibrate the calorimeter. Calibration means you have to know how much heat that this calorimeter will absorb. You have to determine the specific heat of the calorimeter. Whether it's homemade, whether it's manufactured, we have to know how much this calorimeter is absorbing. And that's part of the experiment itself. So the first thing here, we'll do the specific heat of the calorimeter itself. So in the sense will determine not direct but indirect. So let's do this one here. Can I take this one out? Can I take this one out?
Yes, yes.
Okay, so I'm trying to maybe split this here in two, so you can follow me with this with the calorimeter stuff here, the structure of the calorimeter here. I don't know where that really is. Just hold on, we'll find it. Yeah, here it is. So I'm going to split here a little bit. Okay, so I'm splitting this one here and splitting the to this one here. So 2 and 2. Okay, so this one is not splitting. Okay. Okay. We got them split, so I can follow both sides at the same time. That's very good. So now we have a calorimeter here. So the first thing here we'll have, the first procedure is the heat capacity or specific heat of the calorimeter. Or you can call it heat capacity or specific heat of the calorimeter. How much is this calorimeter is absorbing? So that's we will have this calorimeter here. The stirrer is as you can see, this is your stirrer from your area here. Thermometer inside your drawer, alcohol thermometer. So, Ms. Martinez, could you erase this one here? Here's the whole thermometer. Can you see it? That's in your drawer. We are not using any mercury thermometer because we have problem with cleaning them up. We have a lot of accidents. So we have just an alcohol, which is easy to clean up if it's broken, correct? We have only the alcohol with the coloring inside. So they use ethanol, but just red dye inside. Show how it shows up. Alcohol is colorless, but you have to see how much it goes up. They put the dye there. So what you will do here in this calorimeter here, we will be using hot H2O and cold H2O, correct? So you will have two. You will first you prepare your cold. This is ice here, okay? And you can put inside a little bit of ice. You can put maybe around 200 ml of your of distilled or even tabor. Tabor will work. So you cool this one here up to 4 to 6 degrees, but you have to know how much is it, correct? So we'll be using the tabor inside. Inside this cold one will be our cold tabor, correct, guys? And then we can warm at room temperature, so we can measure the temperature at room temperature here. So here it is. Let me have this one here. It said I told you 200, but 200 you'll use it the whole thing. Put more than 200. It says here 250. What's happened is then we will have a flask here. We have exactly the flask, volumetric flask here, which will read at the marker here 200 mL. So maybe he's telling you just put 250 just in case. And then you'll transfer the temperature 4 to 6 degrees inside this to the level here. What's happened here, we are in the formula here, we are not using the milliliters, we are using the density. Since the density of H2O is 1 gram per ml, 200 mLs of H2O is 200 grams of H2O, correct? So this, because of the density, is 1 gram per ml. So 200 mLs of H2O equal 200 grams. So to this marker here. And the temperature, you have to measure it 4 to 6. You put it inside this calorimeter. Okay, so inside the calorimeter is the cold 200 mils of cold H2O. Now you have the stirrer here, you have the thermometer, you can read the temperature when you are ready. So in the other one, you will have to prepare room temperature one. So just take a beaker here, has the beaker, so don't worry, maybe 250, 200 mils. But then you have another flask here, is 200. If you don't have another 2 flasks, then you can use this one here. Just dump the cold first, and then dump the warm here, and then measure the temperature of the warm here. So you put the 250 tab water here, and then you will fill it up to 200 markers. That's 200 grams, 200 mils. But you have to measure the temperature of this. You have to know the temperature of the warm one. Okay, guys. So now I know the temperature of the warm. I put this one inside before the mixing, before taking the lid out, putting the warm into the cold. So warm H2O, that's in your hand. Cold H2O inside. But before I'm doing this, I have to measure what's the initial temperature of the cold H2O. And then I know the temperature of out, which is the temperature of the room, of the lab room, correct? Dump the whole thing inside, and you observe the thermometer temperature will go up, and stays for a few seconds, or maybe 1 minute or 2 constant. It will not go further. That will be your what? Your T final. T temperature, final temperature. The measured here, the cold H2O, T cold initial, correct? And the warm is T initial warm, T warm initial, correct? So how many temperature will you have? You will have 3 temperatures. The temperature of the room temperature of H2O, okay, that's the initial one, and the initial of the cold, and then when you mix them together, they will come to equilibrium of temperature, which is constant. It will remain, but about 1 minute or so. It will not go out. You will see it's not moving. And then because it's, the whole thing, the whole lab is cooling, so it will go drop down, down, down. Correct? So, but it will go up first, because the cold H2O is around 4 degrees, and maybe the room temperature around 21 degrees. So the cold will raise the temperature of the cold to whatever couple degrees. Then you have to look at the final degree. Correct? So we have 3 temperatures here. So this is the first part. We are measuring what? The specific heat, the heat capacity, the specific heat of the calorimeter. So now can I take this one out? Let me now go for the formula. Okay? Take this one out. Now the formula here, I have 2 systems. The heat for the hot or the warm H2O, okay, because warm H2O will lose the heat. Then the cold H2O will gain this heat, correct? That's different from their approach. Their approach for you may be confused, but if you know it this way, every time the hotter one is minus, that's the one is losing the heat. But the heat, its energy, it does not have a value number. Heat is always positive, but we designate losing and gaining. This is gaining, but the value of the heat is the value of energy. It's always positive, correct? So this is losing. That's what it means. The hot ones are losing the heat, the other one, but all in all, heat's always positive value. So now I will specify this one here will be mass of the warm, correct, multiplied by the specific heat of the worm, correct, multiplied by delta, then let's see, T final of the worm and cold, because that's equilibrium, correct, minus T initial of the worm, correct, and this is delta TF, delta T worm. Okay, guys, and this is losing, but don't worry about that, the negative will go out, but this is losing. The other one is gaining. Mass of the cold multiplied by specific heat of the cold, correct, multiplied by T equilibrium, which is T cold, that's the final here, which is cold, and then the warm, minus T initial cold, plus, now here the calorimeter will come with its heat capacity, with its specific heat, multiplied by the specific heat of the calorimeter, multiplied by delta T of the cold here, because everything absorbed where? The cold tab bar is inside the cold, so it will be T W T final WC, that's equilibrium, minus T initial cold. So, okay, guys, so the mass here we say 200. This is our 200 grams, correct? So make for significant here 200 grams. The mass of the cold, we took the same thing, 200 grams, correct? The specific heat of H2O on both sides are equal, which is 4.184 joules per gram centigrade Celsius. Both of them are equal, correct? So both of them are 4.184 joule per gram, because both of them, tabor, does not really matter if it's liquid, warm or cold, this is the same specific heat. So now, the only thing you will measure this one here. Let's put this one here. You are measuring this one here, the equilibrium whole thing, that's you don't know. This one, you measure it at the initial for the cold, and this one, the initial of the warm here, of the warm. So this is warm, and this is cold. Now solve for the specific heat of the calorimeter, or the heat capacity of the calorimeter. Okay, guys? So this is the first part. The first part is very crucial, because then it will come with you all the time. But before we start anything, we have to determine how much heat is absorbed by this foam cup, or what is homemade mug cup or calorimeter. Okay, guys? So everything is there. Everything is there. Specific heat of the warm is equal to specific heat of the cold. That's number one. Any questions so far? Any question? So that's the first one, is very important, and you will do it one trial, that's all. Okay? So when I have this one here calculated, then everything will be easy for me. So the next one here is determine the specific heat of a metal. So now the metal, I saw they have a metal shots of aluminum, I think. So of aluminum. So can I take this one out? Take it out? Okay, so this is the first one. As I said, I might have this, if you look at those here, might have this, I take the picture here out. You can see it's different. There's their specific heat. Mine is capital CSP. They have capital heat, specific heat SH, abbreviation of specific heat. Specific S, heat is H. So it doesn't matter. This is the same thing. So you calculate the specific heat as we said. Then the next one is the specific heat of the metal. You will do the same thing we did, but now instead of hot and cold, you put the H2O at room temperature inside, not the cold. Okay, so here the second one. Let me just go for the second one here. Here it is, guys. So here it is. So what we have to do in this second experiment. The experiment is three components, 3 sections. One trial more than enough, because as I said, the whole thing is not that accurate or that precise. So here, look at this. We will have a metal. So the metal is shots. So it will be very hard to weigh and very hard to handle. So what we will do here, you will get a test tube, larger test tube, the largest ever you have, larger one. And then you will put your weight empty first. You weigh it empty. Okay? Now you ask me how you weigh this one here, and you might not be able. So the best thing is you have small beaker. You tear this beaker here. You tear the weight. You tear the mass here. The mass here of this small beaker. So, and then you put your larger test tube here inside, and then you weigh. You will weigh just the test tube. You don't need to weigh the beaker. Just the test tube empty. You need what? Empty. Now, after that, you will start putting your metal inside. So after this, I'll put my metal. I think I saw it is metal shots. Whether it's metal, cylinder, whatever its shape, it does not really matter. So this is my metal here inside. Okay? And then after filling this one here, my metal shots inside, those, I think they look like aluminum. You can have one metal shot in your hand. If it's very light, that's aluminum. So it's very, very thick, very heavy. That will be lead. That's what we have inside the lab. Lead and aluminum, they might look alike, but the density is different. So this is the, now you go and reweigh. This is empty here. We said empty. Reweigh the filled test tube. Now, the same thing. Use the beaker, tear the beaker first, and then put the filled one here. That's the filled one. But you have to get rid of tear the whole thing. You have to get rid of the beaker mass. Beaker mass is out. We don't need it, okay? So we need just this one. Reweigh. The difference between weighing will give you what? Difference will give you what? Yes, mass of the metal. Now the metal is maybe a shots, I don't know, it looks like shots. But anyway, so mass of the metal, we know the mass of the metal, correct? Everybody agrees? Now, after I'm done with this, I have to use what? Hot plate. Hot plate. So then I have to get a beaker, small tiny beaker. I put mine, the tabware here. That's to boiling here. I have to bring this tabware to boiling, but I can put in the meantime my shots inside, and the beaker with the shots inside. Maybe have another color. This is my beaker here with the shots inside it. So I boil it for 10 minutes, maybe 15 minutes. It'll tell you a couple of times because you have to take the temperature of it. So I need to see it that's about 100 degrees Celsius. Okay, so the best way is at the beginning, crank the whole thing to the end. That's the heater here, heater dial. So, and this is stirrer, so keep it off. We are not stirring anything, so keep this one off, and this one on to the end of it. So it will go up to 300 centigrade Celsius. So it will be quick, boiling quick, so you don't have to wait longer time. So we need to measure the temperature here. How much? 100 degrees. Keep it under 100 degrees, and then before you use it, measure the temperature by inserting inside the test tube, not the beaker. Avoid any drops of H2O inside this test tube, because that will affect your mass. That will affect what? Your mass. So now we know the mass of it. We keep it boiled 100 degrees for 10-15 minutes, and come and measure the temperature. We come back again, give it another 5-10 minutes, 100%. And meantime, we can prepare our this one here. We can put this one here 100 mils of just normal tap water. At what? At room temperature. At what? Room temperature. Okay, guys? So, I measure the temperature here, room temperature. I have to measure the temperature here. Oops, sorry. I have to measure the temperature of our homemade calorimeter here. See how much is the temperature inside before I start. Okay, a couple of times maybe. Make sure one reading, two readings, just for yourself to make sure the temperature is not going back and forth. It's constant temperature, which is really the room temperature, correct? Now I'm ready here to take the lid, okay, to take the lid out and transfer all the shots 100 degrees. Very quick, don't delay, because you delay, the cold air will cool down the 100. It's no longer 100, maybe 95, 96, and that's part of the error, correct? So transfer all the metal here, and then with the stirrer here, you just keep stirring. Anytime you add, like the first experiment, you added the warm H2O, stir, so, and then see the temperature will go up. Here, when you add this hot 100 degrees to 100 ml of room temperature H2O, and stir, and you see the temperature will go up, 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 and then will stay for 1 minute or so, constant. That's our equilibrium. That's our equilibrium. That's final temperature, equilibrium temperature, where the hot 100 degrees is equalized with the room temperature of the calorimeter. Correct? I record that temperature. We need to record temperature of the thermometer after mixing this hot metal, or this hot metal shots. Okay, guys? Now we'll do the same thing we did. Okay, guys? We do the same thing we did here. And can I take this one out? Now calculation, because what we are getting out of the calorimeter is the final temperature, correct? What we are getting out of this tube is the initial temperature of the hot metal, or the metal shots. So now we just plug in the same formula we did before. Are we just following? The same thing. So I might do it differently and different symbols, but we are in the same way. So here it is. I will say here it is. This is minus Q, which is losing the metal or the tab or inside the calorimeter. The metal is losing the heat, correct? Then this minus Q metal. The metal is losing the heat, meaning that's losing heat. Okay? Losing heat. And which is gaining the room temperature H2O. And you do the same thing we did. The one is this metal is heating. What's the Q? Mass of the metal multiplied by the specific heat of the metal, and that's what we are at. That's our goal. That's what we are looking for. So here it is. That's our goal. That's what we have to calculate. Correct? Multiply by delta T. Delta T is T final, which is this time is coming from the metal, and H2O. Okay, that's delta, minus T initial of the metal, correct? Which is around what? We said around 100 degrees. You have to measure it. If it's not 100, you feel it that it's 99 or 98, just record the real one. I said ideally we want to see it 100 degrees, but if you feel that you are reading off a little bit, but write the true one. That's the boiling one, correct? That's the boiling one. Initial metal boiling temperature. And this will equal to mass of H2O at room temperature. How much we added? We added how much we said? 100 ml. How much is the mass of it? 100 grams. 100 grams, correct? Because the densest one, this is 100 gram H2O at room temperature. Multiplied by specific heat of H2O at room temperature here, room temperature, which is again 4.184 joule per gram centigrade Celsius. Multiplied by delta, which is this one here, T final, T equilibrium, T final, which is metal and H2O. That's you read after mixing. This is after mixing. Minus T initial of H2O. That's a room temperature. That's room temperature. Room temperature, correct? Okay, what's missing now? We did use this one here for the specific heat of the metal. What is missing? Plus, see, all this here for H2O. All of it is for H2O. But there is portion of the heat will be absorbed by the calorimeter, correct? Will be C, specific heat, determined from the first step we did, the beginning, correct? That's determined specific heat of calorimeter. Here, determined before. Determined at first step of the experiment. Correct? We did it at the beginning. We have to start with this. Specific heat multiplied by the same thing here, the same TF final, which is the metal and the H2O, minus the T H2O initial at room temperature, initial. Okay, that's the T final here. So this is the T final after mixing. This is the initial room temperature of the H2O. This is the T final of the after mixing. Initial metal temperature is around 100 degrees. Specific, that's the only thing you don't know. The metal you have weighed by the test tube, weighing test tube empty, then you fill the test tube. The difference gave you the metal itself. Let me show you their formula, might different, but this at the end is the same thing. So here it is. Oh, it should be here somewhere. Well, I don't see it, but they might have put it there on the way to the top. So yeah, here it is. You can see it. I can show you where this really is. This is here. This is here, guys. Correct, guys? This is the same thing, but different designation. I said room temperature, they said W, whatever, but this is the same thing. This one here has to be determined first, the specific heat of the calorimeter or heat capacity of a calorimeter. This is the cold H2O, this is the mass of H2O, mass of the metal, specific heat of the metal, and they just run it through, divide both sides by the mass of the metal and the delta T. So if you divide it by mass of the metal and delta T of the metal, then you isolate the specific heat. I put in specific heat as CSV metal, correct? So that's the specific heat of the metal is now given to you. See? That's the specific heat. Okay? That's specific heat. Well, somebody will tell me it has spot an error. Somebody has spot an error, an typo error. Come on, look at it again. Where's an error here? There's an error inside their formula, and this is can make a big mistake. We divide this one here by what? By this Tm, by the T equilibrium, final equilibrium temperature, minus the initial temperature of the metal, correct? But here they divided by the H2O. That's wrong. The M here is not correct. It has to be Tm, which is here, correct? They did here by TW. That's a typo, guys. So correct this typo here, please. Correct this typo. See, this one here has to be Tm, the metal. That's related to the metal, not TW. Not TW. That's a typo. That's T metal, because they started correct with it. Started correct here. Mass, specific heat of the metal, multiplied by delta T of the metal means final equilibrium minus initial heat of the metal, which is 100 degrees. And you put the minus there, so the minus cancels out. See here this, and they just rework it out, and this is mass of the metal multiplied by 100. See here, that's here final temperature minus 100 degrees Celsius, correct? That's the initial of the metal itself. Okay guys, and then you can determine the specific heat of the metal, and I can check what the metal is, and then get you can see, you don't have to submit it, but you can see how good your data is with this calorimeter. I doubt you will have a very precise or very accurate, if I give you the literature value, a very accurate value, but you will be close within maybe 20% or so, or 30% error. So, but yeah, I'll give you this, I'll check the metal charts over there. I think they are aluminum, but I'll check. So the last thing ever last is you do what? The ice pack, correct? Now this is, can I take this one out? Did you correct the formula? It has to be T, delta T, not W, delta T M, because you divide both sides by this one here. So I don't know what's happened here. It's supposed to be stuck or something. Okay, so it's not moving anywhere, so it's stuck somehow. Well, I'm trying to get it moving, but it's not moving anywhere, so. Well, let's do the third one here, but it's not moving at all, so I don't know what's happened to it. It's frozen somehow. The third one is the heat of solution of the ice pack, which is ammonium nitrate. You will have the same, I can't move anywhere to any one of those, so maybe I'll escape this one here. Okay. Okay, so here it is. It's moving now. I hope it's moving now. So let me see if it will delete the whole thing. Yes, it's moved. Well, it's stuck and then escaped. It's working. So we did this one here. Now the heat of the reaction. Not really the heat of reaction. It's a reaction between ammonium nitrate and H2O. So here it is. Just to show you the. As I said, one trial more than enough. This is the ice pack here. This is the ice pack. You have H2O here in the bag, and all of it is no, that's the H2O, yeah. And here is crystals of ammonium nitrate. So I'll tell you to tap this one here a little bit, to burst it, so the H2O will come and then react with this. So ammonium nitrate solid will react with H2O liquid to give you ammonium nitrate, okay, aqueous plus H2O. H2O will be as a solvent there, but here is what we are interested in. This reaction is plus heat here. It's an endothermic reaction, so the whole bag will feel very, very cold, correct? Because absorbing the heat to dissolve itself in H2O. You get at the end ammonium cation nitrate, H2O still there as a solvent there, but the heat is an endothermic, it acquires the heat. So we have to determine the heat of the solution, not really the reaction. It's a chemical reaction, yes, but this can be reversed, correct? Can you see? I can evaporate H2O, I can get the crystals back, but I will say heat. The correct one is heat of solution. because I make out of crystals of ammonium nitrate, the endothermic, I made of them solution. So its heat of reaction is correct, that's general, but very specific is solubility, heat of solution. So we have to determine what we have to determine the what they call it. We have to determine the this heat of solution. Now, one of those is I have to know how much grams of this I'm using, the mass of this. Correct? I have to know how much I use. Then with the help of the molar mass, okay, I transfer the whole thing into joules per mole. So this is the heat. So I'll get the heat from the calorimeter, but then I have to divide the heat per mole. Okay, guys, I'll determine the heat, this one heat here, from the calorimeter calculation, from calorimeter experiment. But then I have to relate this one here to moles of this ammonium nitrate. How I turn this one to moles? I have the grams of the ammonium nitrate, divided this by the molar mass, I get number of moles. Then whatever heat I got from this, I can what? I can get divide the heat by the number of moles, correct? So that's the whole idea, is to get the heat of the solution. So can I take this one out? Everybody has it? So that's the whole idea. So that's the whole idea. So we'll take, they have calcium nitrate or calcium chloride. That's an exothermic. The heat will be the other side, in the product side. But we'll take, I want you to have the ice bath experience. You will see the calorimeter feeling at the bottom very cold. You can touch the bottom of the, after mixing, you will see it yourself. So what you have to do here, again, you have inside the, where is the, here's the number of moles. After you are done with the Q, you divide it by the number of moles, correct? So here's the what we have to do. Here we have to look into that. So here it is. You fill this one here again by our 100 standard, like 100 mils of room temperature H2O, correct? Which is 100 grams, correct? That's here 100 mils of H2O, correct? And even whenever you are mixing, then always stir. That's your thermometer, that's your stirrer. So now you will weigh a certain amount. I think you will weigh about less than 1 gram to see. But if you want to see more, then it will be like, let me see here. Yes, here to see. That's the heat of the capacity, so we are. Yeah, heat of the solution here. Let me take this one here out. So here it is, guys. You will weigh, first you will fill your thermometer with 100 mils, correct? 100 mils of thermometer is, and then about, I said 1 gram. Less than 1 gram, you can't see nothing. You can't see. But here you can see, they tell you about 7.85 here. Guys, here, look at this. You will weigh out of these crystals here. You have these crystals here. You can see it, ammonium nitrate in the ice pack, and ammonium nitrate is a very good what? Somebody will tell me it's good for. Somebody is planting, do some roses or some plants inside the backyard. That's a fertilizer, an excellent fertilizer, ammonium nitrate. So ammonium nitrate is an excellent fertilizer. And this ice pack is an endothermic. So you will weigh about 7 to 8.5, but you have to know exactly. So between 7.5 to 8.5, and they say they prefer to 7, but it does not really. The more you weigh, even 10 grams will work. The main thing is I want you, and they want you, whoever have written this, to touch the bottom of, after you mixing, you will feel it cold. If I put 1 gram or half a gram, I will not feel that cold. But if we put 10 grams, it will work too. It will work. So, but then that's what you have to weigh this one first, the ammonium nitrate. So you have, hold on guys, that's what you have to weigh. If you weigh 10 grams, that's fine. You can feel the whole thing. So the mass of this ammonium nitrate has to be, if you weigh 10, you have to be exact 10 moles, correct? You will measure the temperature of what? Of the H2O inside. You measure the temperature of H2O inside, correct? So here it is, the formula of this, the same thing, is totally different from what we have before. Although the calorimeter will be there, but we have to see that will be a different. Here it is, guys. Specifically, they did not put you here it is, guys. So this is the formula you will be using. So this is, let me just, this one here, 2 holes, 1 thermometer here. And this one hole here, stirrer. 100 grams, 100 mils, don't weigh 100 mils H2O, which is 100 grams, correct? And then you have about 7, you have to weigh exactly 7 to 8, say 80 gram of ammonium nitrate powder. So you can weigh it with the weighing dishes. We have small tiny plastic weighing dishes. So, and then you'll measure the temperature you started with all the time. That's your initial one. Do we have to measure the temperature of the ammonium nitrate? The answer is no, no need. It's a room temperature. Then when you open the lid and you start putting this powder, 8 grams, add this under continuous stirring. Continuous stirring. Put the cover there and then keep watching the temperature. Now, this temperature will not go up. If it started at room temperature 22 degrees, correct? It might fall down because it's endothermic. It will fall down maybe a couple degrees. If you have more, you will see degrees more. So if you put, you can do second trial if you wish, do 10 grams. Then you will see it drop like it will, like if you have 8, maybe about 17 degrees, 4 degrees or something, it will drop. It will then at the bottom very cold. Okay, guys? So then you will put your formula here, because you don't have this ammonium nitrate is not losing, correct? So the heat of the solution is Q. The heat of solution is mass, this time total mass, correct? You have 100 grams and you have what? 8 grams, correct? Total mass, specific heat of H2O, which is 4.184 joules per gram centigrade Celsius. And now the only thing is you have to watch the temperature, where did this go? So you have T final minus T initial. Now, since I told you this is the initial will be higher, so you'll get negative. But since it's endothermic reaction, this you can put the minus. So don't worry about the minus coming here. The whole value of this will be positive, correct? This endothermic reaction, the heat will be positive, not negative. So you can have this final after mixing. This one you started with the tabor at the beginning, 21. When you mix, maybe it will drop. This is endothermic reaction. It will drop a couple of degrees down, depending on the amount. If you have larger amount, it will drop even further, maybe 15 degrees, maybe 14 degrees. The more you add, the more it will drop down, and you'll feel how cold that really is. Okay, guys, that's the third. So I'll stop here. And we'll do one trial. That's more than enough. Okay, guys, we'll do one trial, and we don't need more than one trial. Here they tell you, I think it's double trials or twice. No, it's just, let's look at their data. No, they use just one trial. Yeah, they use one. Yeah, they use one trial. And we'll not use both salt. We'll just one salt. I want you to feel the cold. Okay? Let's start, and if you have any questions, then you can ask me during the lab itself. Thank you very much. Let's start. And don't forget the attendance sheet, please. Thank you.